All right, good morning, everyone. I've just hit the record button, so our session is now being recorded. So the plan for today is to cover some fundamental mathematics that you may or may not have seen to the detail that we're going to present it, but you're certainly going to be familiar with it. And this fundamental mathematics is what we're going to need moving forward in this course. So we saw on Wednesday's class that when we start to play with the puzzles and the swap puzzle and the various moves, that questions of solvability versus unsolvability were somewhat tied, at least it seemed, were tied with whether the number of moves to solve the puzzle was even versus odd. So there's sort of some number theoretic results at play. There we just saw it was parity related, so odd or evenness. But we'll see that it can run a little bit deeper. It could be related to divisibility by other numbers and things of that nature. So the foundational mathematics that we're going to need is the theory of numbers, so divisibility of integers and prime numbers and what is known as modular arithmetic, which I'm not sure we'll get to today, but we'll certainly get to it on Monday. But even before that, this notion of a set, a collection of objects, and whether an element is in the set or not in a set. So that's our goal for at least today and possibly some of Monday's class, is to get through some of the preliminary mathematics that we're going to be building off of. Now, one of the reasons I want to do this is to sort of set the stage as to what is the background material that we're going to expect in this class. You're coming into this class, linear algebra was a prerequisite, and you may be thinking, okay, how much linear algebra do I need to remember? Well, it turns out none. We're not going to be using linear algebra. Linear algebra could have been used in the first puzzle we were looking at, which was lights out, but we're not going to cover that puzzle. And in terms of the rest of the class, no, we're not going to use linear algebra. It's not that because there's any slight on linear algebra. The reason it was a prerequisite is, one, we have the potential to use it if we need to, but two, what it does is it establishes that you have a certain mathematical maturity now coming into this class. You've seen material that is not just from the calculus stream. It's not just about functions and graphing and rates of change. You've seen some other mathematics as well, linear algebra and geometry. And so it's about having some mathematical maturity. And that's what we're really going to need for this course, is the ability to deal with objects that we might not have dealt with in this way before. And so that's really one of the reasons why linear algebra was required. It's to set a level of expectation in terms of the kinds of math that we're going to see moving forward, and having an open mind to accept these other kinds of mathematics. But to answer the question, okay, so what is it that you really need in this course in terms of concrete mathematics? Well, that's what we're going to lay out today. So let's get started into that. First thing we're going to need is this notion of a set. So what is a set? Well, a set is just a well-defined collection of objects. We're going to have sets all over the place in this course. Everything we're going to be turning into sets. Mathematicians like to turn things into sets because it's essentially like it puts a bunch of stuff in a bag, and then now I can talk about the bag that contains all of these things. So sets are very handy for us to sort of put the scope of what we're talking about into place. The elements in that set, or in other words, the objects in the bag that we're considering, are known as the elements. Okay, so we've got sets, and we've got these things that are in those sets, which are elements. Conventionally, we use capital letters to denote a set and lowercase letters to denote the elements of the set. And we've got some special notation that we use to denote whether an object is in a set or not. And so that's this next line. If little x is an element of a set capital A or big A, then what we write is we write little x, and then we write this sort of funny little backwards E kind of symbol, and A. And that backwards E symbol that's red is an element of. So we read a statement like X is an element of A. If we have an object, Y in this case, and it's not in the set A, then we use that same symbol, but we use a slash through it. And that's read not an element of, so Y is not an element of A. Okay, so that's how we're going to talk about things being in or not in a set. How do we define a set? For us, we're going to define sets in two ways. We're either just going to explicitly list them by writing them, the elements, in between curly brackets. So for example, we could do A is 1, 2, 3, 4, closing curly brackets. So A just consists of the set of objects, which are the integers 1, 2, 3, and 4. And so we could, for example, say, well, 2 is an element of A. But 5, oh, sorry, I said is an element, and then I slashed it out. 2 is an element of A, but 5 is not an element of A, because 5 isn't in that set. As another example, maybe we'll look at a set B. And here we can add some extra layers to this. So B is a set. And what are the objects in the set? Well, so far the only set example I've given you are where the objects are coming from the set of integers. But you can think of this set as, again, it's just like a bag that holds stuff. What kinds of stuff can you put in it? Well, anything. You can put any mathematical object in it. So we put numbers in it, 1, 2, 3, 4. But we really can put any objects we want into a set. So for example, I could put another set as an element inside a set. Now, maybe I'll change the color here. So there's our first element, and there's our second element. So there is a set B. It has two objects in it. The first object is the set containing 1 and 2, and the second object is the number 3. So what I have is that then 1, 2, that set, that is an element of B. I have 3, that's also an element of B. But 1 is not an element of B. 1 is not an element of B because 1 is not in that list of objects. There's only 2 objects in B, that purple thing and that green number 3. And neither one of those is equal to 1. So that's just some subtle points. We can start to layer these ideas on top of each other. Sets can contain any objects, and therefore they can contain other sets. So that's one way to build sets. Another way to build sets is to use set builder notation. So what is our set builder notation? Our set builder notation looks like this. I'll take the name of our set, which I'll call it A in this case. And what I'm going to do is I'm going to build the set by stating properties, or a property that an element has to have in order to be in that set. So we write it as follows. We say it's going to be the set of all x, whatever x is, with a vertical bar. That vertical bar is going to be read such that. So we read that as such that. So this is A is the collection of all x such that x has property P. And that's set builder notation. So the way we read this is the set of all x such that x has property P, whatever property P is. So as an example, maybe I'll say, well, maybe I'll change the name and I'll call this set E. And what it is, it's the set of all x such that x is an even integer. And so there's our set. So what are the elements of this thing? Well, there's going to be infinitely many of them, but they're -6, -4, -2, 0, 2, 4, 6, ... So I couldn't really employ one, the way of building it using one, by just writing the elements between curly brackets, because there's infinitely many elements. And so I'd have to use sort of this ... and hope that you would be able to infer what the pattern is. It might not be clear what the pattern is with just a few examples. So this is where the set builder notation comes in. It completely characterizes what it means to be in the set. You've got to be an integer and you've got to be even. Okay, so that's set builder notation. Some of the common sets that we're going to be encountering in this course are the following. The integers, which we denote by capital Z. And the one thing to note about that capital Z, in fact, all of these things, these special letters that denote sets, they all have some doubling up somewhere. You notice that if you can sort of look very closely, maybe I'll zoom in a bit. If you look at that Z, there's a double diagonal bar across, and same with the N. And the Q, it's got some doubling up as well. That's on purpose. That's our standard notation for sets. So the way we would do it by hand is I would write a Z like that. For the Q, typically we denote it by that with this sort of double bar on the left-hand side. R is denoted by this double bar and then the R. So those are special symbols that denote these sets. These set of integers, which is shown there, which are all the negative and positive whole numbers. We've got the natural numbers, which are the non-negative integers. So 0, 1, 2, and so on. And then we've got the set of positive integers, which is just the set of the natural numbers with the 0 removed. So it's 1, 2, 3, and so on. You might have heard these as called the whole numbers before. Well, one of these, I shouldn't actually write this down because there's that's not a conventional name, the whole numbers. Sometimes people refer the whole numbers to be the one with the 0 in it and all the positive integers, and sometimes people refer to it to be just the positive integers. The whole numbers is not a technical math term. The technical math terms are natural numbers and positive integers. So we've got our natural numbers, 0, 1, 2, 3, and so on, and our positive integers, 1, 2, 3, and so on. We've got our rational numbers, which is denoted by that Q, and that's just the set of all ratios of integers. So these are the fractions, if you want to think of them that way. And then again, with the superscript of the plus, those are the positive rational numbers. Then we have our real numbers, which we've been dealing with for well, almost our entire lives. We deal with the set of real numbers. And then the last set there is a set that's really important for us. It's just a finite set of integers from 1 to a value n. So for example, if I had, say, left square bracket followed by a 6 and then a right square bracket, what that is going to represent is the set of numbers 1, 2, 3, 4, 5, 6. Why is this important for us? Because those are going to be the set of tiles and the set of boxes for our puzzles. Right? For the swap puzzle last day, we were interested in square bracket 8, or the set of integers from 1 to 8. And we're going to be interested on how those set of numbers get moved when we permute the pieces of the puzzle. So this is going to be our set of interest for us. A couple more things to do with sets, and then we'll get into integers. Again, I don't think any of this is probably new to any of you. This is just a review, so we're all on a common footing for the kinds of objects that we're going to be needing in this course. But there may be little nuggets that are new. For example, this square bracket 6, or square bracket n, denoting a set of integers from 1 to n. That might be new for you. So let A and B be sets. If every element of A is also an element of B, then we say that A is a subset of B. And we have a special notation for this. We use capital A and then this inclusion symbol, B. So that is read a subset of. So A is a subset of B. And there's some notation. Some people use the notation if they're equal, then they'll put like a sort of a less than or equal sign kind of analogy to this. They'll use this sort of curved inclusion symbol and then also an extra vertical or horizontal line below it to possible inclusion. We're not going to do that. We just have the one symbol for subset. A could be equal to B in this case because A contains all elements that B contains if they are equal. So, and set is a subset of itself. If for the next one here, so if A is a subset of B and B is a subset of A, then what does that mean? So what did this mean? If A is a subset of B and B is a subset of A? Yeah, it means they're equal to each other, exactly. It means they're going to be equal to each other. Typo, yeah. So I'm just reading through the chats again, and are we going to be deducted a mark if we do not follow the way to write those set letters? No. So I mean, if you didn't use the double vertical bar notation or things like that, we're not going to be super picky on that. The only thing is that these are conventional set names. These are set names that are used all around the world. So it is a good idea if you want to communicate with other people about the same ideas that you speak in a common language, and this is that common language. So these set letters are the common language. Everyone uses these all around the world. The Z is actually from the German word Zahlen, which means integer essentially. So these letters are generated, they are influenced by other languages as well. R, of course, is first letter of the word real. Okay, so, here we are. So we've got if A is a subset of B and B is a subset of A, then that means the sets are actually equal. Now, you may look at this and say, you know, that's a big deal. That seems kind of obvious. But the powerful part of that statement is that if I ever want to show two sets are equal to each other, I just need to do two things. I just need to show that every element of A is an element of B, and vice versa. If I can show every element of B is an element of A, then I can show that they're equal. And that's typically how we'll prove any two sets are equal to each other. If we have two sets and I want to show they're equal to each other, that's how we're going to do it. We're going to show that one is a subset of the other and vice versa. The set with no elements. So the set with no elements is the empty set. You may say, well, why would I consider such a thing? Why do I need a set with no elements? It turns out it's actually a pretty powerful concept, and we're going to make extensive use of this. So considering a set with nothing in it is a very great sort of intellectual leap in the mathematics, development of mathematics. And we denote it in one of two ways. We either denote it by this sort of what looks like a 0 or an O with a slash through it, or we can use the two curly brackets and then just put nothing in between them. So either of those represents an empty set. If you've done any computing science whatsoever, you do know the power of having an empty set, or maybe even an empty list, or an empty string, an empty something of a data object, because that's often how you can initialize a data object in computing science. You just set it to be the empty version of that data object, and then you populate it as you run your program. So this idea of an empty object is quite a powerful tool, and it's used everywhere in computing science, but it's also used extensively in mathematics as well. Some of the things we can do with sets, so we can operate on them. Operate as in provide some operations which allow us to combine two or more sets together in some way. So there's the union, that is, you take everything in one set and combine it with everything in the other set to form one big superset, which they're both subsets of. And then we've got the intersection, which is the set of all elements that are in both the sets A and B. So you can see from this description that the union is essentially related to the word or, and the intersection is related to the word and. So the union is you have to be in one set or the other set, and to be in the intersection you have to be in both sets. You have to be in A and in B. The complement of a set is just everything that's not in a set. So the complement of A is just everything that's not in it. Now this only makes sense when you've restricted your attention to some particular, what we call a universe of discourse. The reason is I could say, you know, what's the complement of my set 6 up above? I've got the set 1, 2, 3, 4, 5, 6. What's the complement of that? Well, from the way this complement is written, it should be everything that's not an integer from 1 to 6. So that means my kitchen cupboard should be in that complement. Well, of course, that's not what we intend. So here we have to be very subtle in how we read this. The complement only makes sense when we've specified where we expect A to live inside. So this requires we think of A as a subset of some larger set called the universe, which is denoted by U. And typically our universes are going to be these sets we named above: Z, N, Z plus, so the integers, the non-negative integers or the natural numbers, the set of positive integers, the rational numbers, the positive rational numbers, the real numbers. Those are going to be our universes. For the most part, that's what we're going to consider our universes. So it'll make sense to talk about a complement. The difference is just everything that's in one set but not in the other. And the difference, the order matters there. So A, the difference of A and B is everything that's in A but is not in B. So that's also written as A intersected with the complement of B. And then the last thing is a product. We can take the product of two sets, and what that does is it just forms the set of all tuples where the first component is from the set A and the second one is from the set B. So as an example, we could do something like 1, 2, A, B, C. So I can take the product of those two sets, and that would just consist of the set of all pairs. 1 in A, 1 in B, 1 in C, 2 in A, 2 in B, and 2 in C. So that's what our product, or it's also known as the Cartesian product, is. Once we have a set, we can talk about its cardinality. These are going to be things we're interested in, of course, and that's denoted by these vertical brackets around A. So that's vertical brackets generally in math always denote the size of something, and size can be dependent on sort of what kind of object you're considering. So if it's a number, you know, putting the magnitude sides around a number really means absolute value. Or if it's a vector, then it would mean magnitude or length. In this case, the vertical bars around A means the size of A. That is how many elements are in it. One of the things we're going to be interested in is we're going to be interested in the set of all possible configurations of the Rubik's Cube. And what is the size of that set? So that's one fundamental question we want to answer, is what is the size of the set of all configurations of the Rubik's Cube? We've got the laws of set theory, which allow us to sort of describe how these operations behave when you start combining them together. Like what if you do a union and then a union, or an intersected in a union, and so on. And so those are just all the properties there. I won't bother going through them in any great detail. It's unlikely we'll need any of them for a particular example other than just the ones that will sort of seem obvious in that there's commutative laws. If you take A union B and you take B union A, then you get the same thing. So they sort of state laws that seem quite clear in terms of how they were developed. But that's just a list of all the kinds of properties we have. Okay, so this this leads us to a fun little problem that we want to try to solve. This is a problem that was off an International Math Olympiad contest, particularly from Russia. So this is a challenge problem, and the question was as follows. You've got the numbers 1 through 9 arranged in a grid on the left, and what you're allowed to do is you're allowed to take any two columns you want and just swap them. So for example, I could take this column, and I could take this column, and then I could just swap them. And so if I do that, then I'll just sort of indicate what happens here. This becomes a 1, and this becomes a 3. This becomes a 6, and this becomes a 4. This becomes a 9, and this becomes a 7. So I've effectively just swapped those two columns. So I can do that, and I can do that for any two columns, just to swap them. The other thing I can do is I can swap rows as well. So for example, then I could swap these two rows. So this would become a 6 down here, and this would become a 9. This is an 8, and this is a 5. This is a 7, and this is a 4. And I just keep doing that. I can swap any rows, any columns, and I just keep doing that. And that will generate a bunch of different patterns of the numbers in that grid. The question is, if I start with the numbers arranged as they are on the left, to prove that it is impossible to produce the configuration on the right, where I will bring your attention to what's happened on the right. 1, 2, 3 are in the same spot, but 6 and 4 have been swapped. And then 7, 8, 9 are all in the same spot. So I want you to just take a minute or two to just think about why it should be impossible to do that. Beautiful response, Karen. So Karen's response in the chat is because you can't modify the original columns. 3, 6, 9 will always be in the same column. So you can't get a 3, 4, 9. Now, I'm going to just add a question to that. So when you say modify the original column, so 3, 6, 9 are always in a column. You don't mean in that order though, right? You mean that 3, 6, 9 they're in the same column, but they could appear in any order. Is that correct? Exactly. The column set will be the same. So that's really one of the observations I wanted to have with this puzzle is that, okay, so we've got this idea of sets and we've developed them. You've probably seen sets since you were little in some of your earlier math classes, sets of objects. But we really haven't done much in probably the way of thinking about sets, whereas this turns out to be precisely a valid problem where just coming up with the notion of a set is the key to understanding how to solve it. So we look at the column sets of the original. I'm using your terminology here, Karen. Column sets. The column sets. So we've got a column set 1, 4, 7. We've got another column set 2, 5, 8. And we've got another column set 3, 6, 9. If we swap two rows, let's say, so I swap the first row and the second row, all that does is it keeps all the numbers in the same columns. It's just rearranging how they appear in the columns. So those column sets don't change. 1, 4, and 7 are still in the same column. 2, 5, and 8 are still in the same column. 3, 6, and 9 are still in the same column. Similarly, if I rearrange columns, those column sets are going to be the same. And that's a little bit more clear because if I just switch columns around, well, I'm just moving the physical columns around, but the set of objects in each of those columns is the same. So these column sets, they're what we refer to as remain invariant. So invariant, fancy word for does not change, under puzzle moves. So these remain invariant other puzzle moves. Therefore, the puzzle on the right, or the configuration on the right, cannot be obtained since it has different column sets. So there's an idea of just using sets to collect information, to collect objects together that have similar or the same properties. In this case, we're using the sets to collect together the objects which live in the same column. And those sets remain invariant. Those sets will never change. Those numbers living in the same columns will always live in the same columns. Okay, so let's go ahead and look at Appendix B. So that was chapter 2 of the lecture notes. Maybe I'll just leave that up in case someone's still copying. That was chapter 2 of the lecture notes, or the notes booklet. And that was just about sets and introducing these fundamental notions. The next one is properties of integers. I put it in Appendix B. I may in the future probably bring it out into its own chapter. But it's Appendix B because it really consists of quite a lot of material that you already know. You probably know in a lot of this stuff since early elementary school, grades 3, 4, 5, etc., and up from there. But just because you've seen it since elementary school, it doesn't mean that it's not important. In fact, these notions are going to be very important for us, so it's worth going through them all again and looking at them with our new sort of advanced eyesight now that we're in our university math classes. We got a keen way to look at problems from the past and make note of the importance of them. And so that's what we're going to do. So the first thing we're going to talk about is divisibility. So here, just a caveat, in this section, all numbers are integers. I'm just reading the chats now. So is that necessary to add the row set in the proof or the column set? So that's a good question. So the question is, should we consider the row sets? You could do an analogous argument with the row sets for that puzzle. You could look at the row sets as an alternate way to view the collection of objects, and that would give an entirely analogous proof with just sort of a view of you tilted your head sideways. So we don't need to mention the row sets in our proof because we just focused on columns, but you could do the same argument for the rows as well. This is a sort of a nod to what we call a duality argument in mathematics sometimes, where you can do an argument one way, but there's a completely symmetric way to do it. And so that way of doing the rows would be, as I said, you maybe just take the transpose of the puzzle. If you take the transpose of the puzzle, you make the column 1, 2, 3 down, and so on. 4, 5, 6 is the next column, and 7, 8, 9. So take the transpose. Then the puzzle is identical to the one we're looking at because we're swapping rows and columns, and those all happen. So you can focus on the row sets as well if you wanted to do it that way. Yeah, so you don't have to do it. We've already covered the proof in this just by looking at the column sets, but that is an alternate way you could prove it. All right, so divisibility. So A divides B. Now this only makes sense when we're talking about integers, so that's for that caveat up above. In this section, all numbers are integers. A divides B, which is written as that A vertical bar B. And again, we're introducing symbols, so I'll tell you how to read them. We read this as divides. So A divides B if we can write B as a multiple of A. So what that means is if I can write B as A times D for some integer D. Okay, so for example, maybe I'll just fit one in here. 3 divides 12. Why is that? 3 divides 12 since 12 is equal to 3 times some other number. In this case, it's 4. So that's how we're going to use this notion of divisibility. Then once we have this notion of divisibility, then we have this idea of the greatest common divisor of two numbers, or what you may have referred to as the greatest common factor. We're going to refer to it as a divisor in this course. So we say that D is the greatest common divisor of two numbers A and B if and only if the following two conditions are satisfied. So this is a definition. So whenever we want to prove something about a GCD or argue something about a GCD, we appeal to the definition. And this is our definition, is that the number D has to divide both integers. So that's step one. Step one is we need to make sure it's a common divisor. It divides both. Okay. But we also want it to be the greatest common divisor. So that's part two. This is the greatest such divisor, or largest. And that is that if there was any other common divisor, let's call it C. So if C divides A and C divides B, then C can't be bigger than D. So C has to be less than or equal to D. That's what it means for D to be the greatest. It's the biggest of all common divisors. Okay, so that's our definition of greatest common divisor. Now, what can we do with this? Well, we can answer some questions about some GCDs. So what's the GCD of 10 and 18? We're going to start small and sort of try to ramp it up if we can. So what's the GCD of 10 and 18? Yeah, we got a 2. 2 is a common divisor, and it's the biggest one. And you may say, well, how do you get that? Most commonly, you probably would have factored these. And you would say, well, 2 is a common divisor, but that's the only one because the other factors are 5 of one of them and 3's in the other one. All right, so how about the next one? What's the GCD of 150 and 105? So take a second or two to work that one out. Very nice. Looks like a lot of people are getting it. Almost less than a second. So we got a 15 here. And again, typically one would look at this as it's a 15 times 10, and this is a 15 times 7. And so we've got this common divisor of a 15, and we can't make it any bigger because the only things left are things that divide both 10 and 7, and there's nothing that's going to divide both 10 and 7. So that's our biggest common divisor. How about the GCD of 35 and 24? What is that? So we've got some guess in there. Check again. We got a 1. Yep, no worries. I like the guesses and then the corrections, because that says you're thinking about the problem. So that's good. Never apologize for making an error. I make plenty of them. Yeah, so it looks like it's 1. Again, we could find this by saying, oh, that's 5 times 7, and that is 2. I'll write it like this. It's 8 times 3, so it's like a 2 cubed times 3, and there's no common factors there. And what we do is we refer to these as relatively prime. There's no common factors, and so we just call them relatively prime. So that's a technical term, and I'll just write it down here. A and B are relatively prime, if and only if their GCD is 1. And that's going to be important for us. We're going to be interested in this property where if I have two numbers, we'd like to know when they don't have any common factors, because not having common factors turns out to be quite a powerful technique we can exploit. And so we're going to be interested in knowing when two numbers are relatively prime. This is not related to prime numbers, though you could kind of relate it back to prime numbers, but this notion of relative primeness just means that there's no common factors between those two numbers, other than just the number 1. Okay, so how about another one? How about the GCD of 2,372 and 2,374? Yep, you could say coprime. Yeah, coprime is fine as well. I will add that in here, or coprime. So how about this GCD? Oh, good. Linda, Karen Veer. Yeah, that's so we've got this extended Euclidean algorithm. It's all right if you're looking at that going, I don't know what that means. We will certainly get to it. The idea here is, how do we know the GCD is 2? Well, one of the things we can know, and so this is the key point. This is why I wanted to do these examples and build up to them, is right now, unless you've seen Euclid's algorithm and so on, right now, if you remember back to maybe where the last time you worked on greatest common factors, perhaps in high school, then the method of choice was to always just factor and find the common common primes, and then sort of extract those out. Kind of what I lured you into the previous few examples. I sort of factored and then found the primes that were in common. Turns out that is the worst way to do GCDs in general. So it's fine for these small examples, but as general practice, it's a bad way to compute GCDs by factoring, because factoring turns out to be hard. Factoring is a hard problem, especially for big numbers. So you may say, well, how big is big? Well, big as in 150, 200 digit numbers. Factoring is hard. In fact, factoring is such a hard problem that the security of transactions over the internet is based upon the fact that factoring is hard. If factoring of large numbers was easy to do computationally, then we wouldn't be able to make our transactions with Amazon, for example, send our credit card information over online, because the way things get encoded, sent over the internet, and then decrypted is built on the fact that the attacker or the hacker has to factor a large number, and that's just a hard thing to do. So we want to get away from computing GCDs by factoring and instead look at another way to compute GCDs, one that's easier to do, at least computationally. And this example that we just did sort of takes a nod in that direction. And so what am I going to do? Well, the first thing I'm going to do is I'm going to write down an equation between these two numbers. That is, I'm going to just write down their difference. And you may say, okay, that's a big deal. So what? Well, this is the key, is that the GCD is a common factor of these two numbers. So the GCD, whatever it is, it has to divide 2,374 and it has to divide 2,372. So if it divides this number and it divides this number, then it has to divide the difference. And the difference is 2, so it must divide this number. So the GCD is either going to, so from this equation, we get that the GCD is 1 or 2. It has to divide the number 2. And then we look at the two numbers and we say, they're both even, so they are divisible by 2, and therefore the GCD is 2. So with a little bit of play, a little bit of exploration, and combining these numbers together and producing new numbers, we can come up with a more effective way of computing GCDs than the factoring approach. Okay. Now I want to get into most of what we're going to do now over the next couple of examples is getting into this idea of trying to find this effective way to compute a GCD. So what I'm first going to do is I'm going to look at this notion of division and remainder. So what is the remainder when dividing 8 into 43? So if I take the number 43 and I divide 8 into it, how many times does 8 go into it and what is left over? So 43 is equal to, I want to know how many times does 8 go into it and what is left over? Yeah, 3's left over, I see that, and we've got that it goes in there 5 times, because 5 times 8 is 40, and then there's 3 left over. So the remainder is 3. This idea of the remainder upon division actually turns out to be so vitally important in mathematics. There's a whole area that's devoted to just dealing with remainders, and this is known as modular arithmetic. And in fact, most of our course is going to be built upon the idea of sort of using these remainders in some way. So before we do that, though, I just want to summarize what this example really says. This example says that if I start with any two numbers, a and b, then I can always take one of those numbers, let's say a, and write it as some multiple of b with a remainder. So this is known as the quotient, and this is known as the remainder. And so in the previous example, 5 was the quotient, 3 was the remainder. So 5 is the quotient. Okay. It turns out that these kinds of operations on integers, division and remainder, are so fundamental that they're pretty much built into every every programming package. So every coding package. So for example, I'm just going to bring up I'm just going to show you how I would get to this. So sage.syzygy.ca. I'll go through next week. We'll spend the first tutorial sort of getting you up and running with this, but this is just sort of a brief overview. You click this link, takes you to a page like this. You sign in with your GitHub account, which you can get for free. When you click that sign in, and it'll take you to a page that looks like this. Yours will be empty because you won't have any files in it, but I've got some files here related to the class. I'll just drag myself over. Then you'd go new, and you can do a Python 3 if you wanted to just work strictly with Python. But for us, we're going to use Sage Math. I open that up, and that takes me to a worksheet where I can do some calculations in Sage Math. So 1 plus 3, okay, there it's 4. That's great. What are we interested in? Well, I had the number 43, and I wanted to know how many times does 8 go into it. If I use this double forward slash, like a division sign, but put 2 of them, comma, or 8, so 43 divided by 8, this is asking for the integer division, or the quotient. How many times does 8 go into 43? And so it comes back with a 5. And then I can also ask for the remainder, 43 and then %8. And that gives me the remainder, which is 3. So that division algorithm that we just introduced, it has 2 things in it. There's a quotient and a remainder. And these things are pretty much built into any computational package, because those are 2 fundamental operations we always want to do. In fact, in Sage, we can do them all at once by using this command called divmod. So I take 43, so divmod 43 and 8. So it first asks for us, do the division and return the quotient, and then use the remainder as the second number. And so if I execute it, it gives me the values 5 and 3. So these are fundamental operations that are going to get used over and over again, and they're in any software package that you want to use. Yep. Yeah, so Python can do that too. In fact, that was Python that I was just actually using. It's kind of, well, we'll talk a little bit about this when I introduce this. It tells me what my kernel is right there. It's Sage Math. But what Sage is a bunch of mathematical libraries built on top of Python. So I have full access to Python right here, but then I can do extra things, like I could say GCD of 150, 105, and this Python doesn't have a native GCD command in it. You can get one by loading various libraries, but we have a GCD coming right from Sage Math. And so it's basically, you can think of Sage Math as Python foundation with stuff, mathematical tools built on top of it that we're going to want to use. Yeah, exactly. You don't have to import anything from Python because it's already there. And one thing you might want to look at is, I don't know if you're going to sort of get a feel for what I'm doing here. I've done this, and yeah, so Brian, you just asked a question. Do you think you can answer it now? Uh, yeah, no brackets to print, which means we're dealing with Python 2. So this is Python 2. For those of you who haven't used Python before and you're wondering what does that mean, Python 2 versus Python 3, it's not such a big deal because you can use your Python 3 print commands as well. But this is Python 2 that this one's actually built upon. And again, we'll go through a little bit more. In next week's tutorial, we'll get up and running with this. Okay, so I'll just wrap today's lecture up in a couple of seconds. So we've got the division algorithm now. And now what I want to do next is focus on using this idea of a division algorithm, so this idea of using quotients and remainders, to come up with an effective way to compute a GCD, which is known as Euclid's algorithm or the Euclidean algorithm. Some of you may be familiar with this from other courses, but we'll summarize it again here. And then we'll also do an implementation in Python just to see how easy it is to implement a GCD algorithm without having to talk about factorization. And then we'll get into prime numbers and modular arithmetic on Monday. And then that'll wrap up all of this sort of preliminary mathematics, the background stuff that we need in order to move forward in the course. And then we'll get into permutations, which is going to start to be how we model our puzzles. All right, so that's it for today. I'm just going to stop the recording now.